Yeah. Just for to learn and share knowledge for ourselves, and that's been happening on this land far before this university. We're standing on the traditional land of the Ghana people and would like to pay respect to elders past, present, and emerging, and I'd like to extend that respect to any Indigenous and Torres Strait Islanders here tonight. Firstly, a few things, and then I'll hand over to Gabe. We have fire exits. There's some at the back, and there's one behind me here. Take this moment to locate your nearest exit in case of emergency. Life jackets under your toilet, under your chairs, in case the room starts to fill with water. Speaking of fill with water, if you need to go to the toilet, we have signs that will direct you there. The women's toilets are quite close, just in the hallway to the left. But after hours, the closest male toilet is locked because it's outside. So the toilets will take, the signs will take to the second nearest male toilets, which is quite far down the hall. I timed it, it's an 80-second walk. So don't leave it last minute. Also, because it's pretty late in the day, at some point, the exterior doors to the physics building will get closed by security. And in that instance, you can still leave through them, but the doors will lock behind you. So if you plan on stepping outside, you need to let someone know to let you back in. And also, after this talk, we'll be doing, remind you, in 121, which is the room at the end of the hallway. We're going to be doing a bit of a socialized, like pizza and drinks, and some physics stuff on display, so that'll be fun, like a year 7 class party. And that's all. Thank you, again.
Thanks, Jacobson. Thank you, everyone, for spending a Thursday evening with us. As Jacob said, my name's Gabe. I'm a PhD student here at the university. And just before I introduce our speaker, I just want to mention a couple of the organizations that helped put this event on. So tonight's lecture is hosted by the Optical Student Chapter here at the university, of which I'm a part of. We're a group of postgraduate students affiliated with the International Photonic Society Optica, which is devoted and committed to promoting and advancing photonics and its applications worldwide. Our chapter achieves this by hosting events locally of this sort, whether it's with students, all ages, or the public. And so just briefly, if I could get the committee members, the chapter committee members, to just put their hands up, firstly so I can thank them, and also so people in the audience are aware that the ones that are going to be running and leading the demonstrations, the interactive demonstrations after the lecture, so people are aware of them. I want to thank the Australian New Zealand Optical Society, ANZOS, the South Australian branch of the Australian Institute of Physics, the Institute of Photonics and Advanced Sensing, and more broadly the University of Adelaide and the Faculty of Science, Engineering and Technology for helping put this event on. We're here to celebrate the International Day of Light, which is a global initiative that reminds us of the massive impact that light has in all of our lives, whether that's in education, scientific endeavor, even art. The 16th of May marks the International Day of Light and marks the anniversary of the first demonstration of the laser by a man called Theodore Maiman in 1960. And the laser is a brilliant example of the power and importance of light. So now I'll introduce our speaker who will tell us a little bit more about that. So Kishan Dholakia is Professor and Director of the Centre of Light for Life at the University of Adelaide, and also Professor at the University of St Andrews in Scotland. He has passion for everything to do with light. His work is cited in the Guinness Book of World Records in 2015, and he's won awards in the United States, Europe, and Australia for his teaching, outreach, and research. He won an Australian Research Council Laureate Fellowship in 2021 and is very excited and about using this award to propel Adelaide into the international forefront of research and teaching on the topic of light. So please join me in giving a warm welcome to Professor Kishan Dholakia.
Thank you, Gabe. Thank you, Jacob, for the very nice introduction and comprehensive list of facilities to avail ourselves. It's a great honour here for me to speak today on this very auspicious occasion about a topic that's really, well, not taken over my life, but it's certainly been a big part of my life for many decades, more than I care to mention. And it's a topic that I think perhaps we don't hear enough about, and maybe we don't really quite know sometimes why light is so important in all our lives and what it might have done. And actually, I wanted to be an astronomer, but I failed miserably for one reason or another, and then I thought I'd set my sights on terrestrial matters. But in a way, as you'll see in this talk, there are examples where now on the terrestrial labs, maybe in corridors, just like the ones you walk past going to facilities, you might be seeing experiments that we, 10, 20 years ago, needed to go to space to see. Anyway, I will do that. Here's a beautiful picture of the aurora. Some of you might have seen it last weekend. I know it's very, it was in the news here. That's not a picture I took. I'm afraid it's Adelaide or nearby. Let me start, set the scene with a little video for everyone.
Everywhere in the world, our days begin with light. Light, you see, is everywhere. Light is life. Light connects us with others, near and far. It entertains and inspires both young and old. Light enables us to see things never imagined. It will drive economies of the future. With light, we can diagnose and treat disease. It helps protect and secure our communities. Light will be key in discovering solutions to society's most pressing problems. And as the lights go down around the world and our days end, our future will continue to be enabled by light.
So that video was made by another very large organisation internationally called SPIE, and it was made in 2015, which was designated the International Year of Light. And the International Day of Light, I guess, is a legacy from that, and the incredible success and visibility light was given. They saw many applications and things, many of which you might have actually performed or used every day, etc. But I can't talk about all of that today. What I can do, though, is give you a snippet of a few things that to do with light. Now, first off, one of the things that's very exciting about light is that we don't actually understand what it is. So it sounds like a conundrum, given it's one of the most researched areas in physics. It's used everywhere, and it's quite trivial to get a light source, turn it on, and do an experiment with it. And I can talk about this at length at the end, but for today, well, light is one of these miraculous things in the universe. In a sense, it has a privileged place. The speed of light is, unconquerable in terms of information capacity and transmission. It holds a special place in the universe. And some people all younger and know that sometimes you call it a wave, sometimes you call it a particle, and how you describe it. We're not going to go into that, but this beautiful experiment on the right, which I don't think we have at the end, but is what some of you will have done, which is known as Young slits from Thomas Young, British scientist in the 17th century, epitomizes what that means. Waves allow us, if you like, to see things such as interference. And if we see a particle nature of light, we lose that interference and see, if you like, something that more akin to something that we might see with mechanical objects in our everyday life. I'm not going to label that, but keep that idea in mind, where the wave is, of course, a wave, but the chunk of energy that might be, if you like, called the light bodies is sometimes called a photon, or a chunk of energy that we might need to use. So what am I going to do today? I'm going to give you 3 example areas, and you'll be pleased to know there's a minimum, if near zero mathematics, I'm going to try and give you beautiful descriptive examples of why light works in these areas, which are 3 that you've actually already seen come up in that short video that I showed. Light for energy, light for measurement, light for light. And light, I'm not the first person to put the trick on the light fantastic. Does anybody know where the word trick for the light fantastic comes from?
Did it Terry Pratchett?
Very, very good answer and nearly correct. Yes, he did write a book like a trip on the light fantastic, but it actually comes from John Milton. And this beautiful poem he wrote called the Aegrae in, I think, 1630, talking about Greek mythology. But it was about a lovely dance that they did. So tiptoeing on the light fantastic. So you'll be pleased to know afterwards dancing is not obligatory for the end afterwards in this talk. So there we go. So that's what we're going to do and talk about. So let's start with that. Let's start with light for energy. So today, many people in the audience may have solar cells in their home. They may have them in their offices. They may have them elsewhere. But solar cells have actually quite literally transformed the way we try and capture energy for humanity and our societal needs. There's not a day that doesn't go by when my phone does not send me a news story relating to energy, climate, and the need to move away from fossil fuels. I imagine it's the same for all of you. And it's also a concern as well. It's a driving concern for young people, all people. But incredibly, the advances in solar energy have been absolutely phenomenal. It's just one example of renewables that are actually impacting what we do. And here we have an amazing combination and intersection between light from the sun, but also understanding material science. And here particularly materials such as silicon play an incredible role. And what we really have is the light coming in and matching what we call energy levels or gaps of energy inside that structure and converting that to electricity. So that's really, really important and it's something that I think you should keep your eye on. Just have a look at this from a week ago, which you may not know from CNN. Solar energy is the fastest growing electricity source in the world. We've now passed over 30% of energy coming out as renewables. So you can see that there. You can see the growth rate there in solar is amazing. All right, so hopefully you're not on this yet. You'll see, and you can see, of course, the coal and gas is still increasing, but the level is dramatically low. So you can see wind and solar increasing tremendously, which is very, very exciting to see. Now, it turns out China is actually at the moment, in terms of its low solar output, the leader. But you can see Australia, it's there. So incredibly, in terms of in the country's output, Australia is actually the world-leading country at the moment, according to this report, for solar energy, which is very exciting for me to see, and bodes extremely well for what we might do in the future. So very exciting to see that generating energy through light at our material side can do that. So that's something that I didn't know, but I'm very, very proud and excited to see that. And I hope those numbers can certainly improve and increase as we move forward. Now, solar power through cells is not the only way we can use light to create energy. Many people will have read about hydrogen. Many people may have other clean energy sources or near clean energy sources. One of the most incredible possibilities, and it is not as far away as you might imagine, is laser fusion. Okay, so laser fusion. So I know, of course, fission and fusion maybe came to prominence with Leslie and Oscar winning movie, but the idea here is that if we can get into this inertial confinement fusion, there's in fact two key approaches. I won't go into that, but pleased to talk to you after the lecture about that. But what we do is have a fusion reaction, not fission, all right, where we heat compress a fuel target to incredible temperatures and we form pellets from deuterium and tritium grade helium and neutrons. Now this actually goes back to the root of what Einstein called a kind of energy mass equivalent, E equals mc squared. Everybody's heard of that equation. But the energy liberated in this way can be potentially untapped. The challenge is to make these pellets super stable, is to make this literally not peter away. And in fact, already, this is Livermore data from a paper just 4 weeks ago in Nature Physics. It shows you that they've actually generated already more energy than fusion energy than they ever did before. It sounds like science fiction, but it's turning into science fact. So we will basically replicate the way a star generates energy on Earth in a terrestrial laboratory and have essentially limitless energy for all. It sounds like a pipe dream or something you might see in a Back to the Future movie, but anyway, it may happen, who knows? It's a pretty exciting time, so watch that space. So, this picture of what I bought in Bunnings last weekend. So, light is not only good for energy, whether it be through solar cells or fusion, but it actually can be used incredibly for measurements. And I'm not talking about this kind of measurement. But the question is, why would you be interested in measurement? And there are many applications and ideas which I won't go right into here, but I'll show you some examples. And I'll show you why light has a phenomenally exciting position in there. This is a picture of LIGO. So LIGO, as I guess everybody knows, transformed our understanding of physics and the universe around us by doing the first clear-cut detection of gravitational waves, already so many years ago now, 8 I guess, and then the Nobel Prize was awarded in physics for that in 2017. And there we have an artist's impression of black holes colliding. What's less advertised about the detection of black holes, it is based on light, and it's based on the idea of interference. Okay, so what we do is we take a device known as an interferometer. So light is a wave, we've already discussed that, and the waves add up and interfere. It's like water waves. And here you see two parts of that interferometer in what's sometimes called a microcell interferometer. We won't go into details today. But what happens is that when you have a gravitational wave, the interference fringes, the way those two water waves or light waves overlap, is perturbed. And a shift in that pattern is what tells us there's been a cosmological event of note emitting gravitational waves. Quite incredible. You know, to grown up in a time when Einstein's theory, and it still is, of course, put under the intense scrutiny. Many people, if you go back in literature, said gravitational waves don't even exist. And yet, bang, we see it happens, and now it's accepted. Now we're just waiting for the app on the phone, right? So that we can detect it and say, oh, they're going to 2 more black holes. Right? So it's incredible what we accept once we see it, but you've got to remember, 100 years or so, there was, and it remains incredible, just I guess, as there is debate today about dark matter and dark energy, incredible debate about whether this actually exists. This is insanely exciting and important, but it was enabled with light. Incredible mirrors, incredible laser systems, powering and making measurements that are quite unfathomable, perhaps, to many people. But very, very exciting to do that. So here in Adelaide, we're proud to have a very strong internationally leading group in atomic clocks. But today, we also need to drive the way we measure time. And actually, that's based, in essence, if you like, on the speed of light, and now is based on a transition in a material like an atom. It's done that way because that's something that, if you like, can be invariant and is not really easily, it can, of course, be perturbed by stray fields like magnetic or electric, but it's something that is, if you like, inherent to that element. And that means if we can measure this transition or jump in energy with light, we can make clocks that are very, very accurate. Today, optical clocks can tell you, if you started a clock at the Big Bang, that clock would only be about 1 second out today. That's how accurate they are. For those of physicists, something like 1 in 10 to the 18. Now you may say, well, I think the watch on my iPhone or Android is pretty good, and I think we're doing pretty well with mechanical watches, and I'd say you're absolutely right. But as we go into interstellar travel, we look at things like communications, GPS, tracking, our accuracy of our clock can make an enormous difference to what we actually do. Okay? And so this is a payload idea that people are looking at. So that's what happens, and we're able to transition between one element in one orbital going up to another, and we do that. And there's the Adelaide team here who keep doing awards every couple of months, which is wonderful to see. But these clocks are becoming essentially portable. They can go and be deployed in field positions. And this is actually good, not just for defense, but for many, many exciting things that we might do. Something else I've been excited about in our measurements here in Adelaide has been measuring interference, not just with two light beams, but with many. So if you ever hold up a laser beam to your bathroom window or a piece of sellotape, you'll get a pattern that looks a little bit like that. Something grainy. That graininess comes about because the light is interfering now. Lots of light waves are interfering. There's lots of light going through your piece of sellotape, and it's scattering and creating what I would call a mess. All right, it's creating a mess. But that mess is very rich in information, and that's beautiful. So if you put that mess in front of a camera, take a camera, put a piece of sellotape in front of it, and shine a laser, that's what we do. And if you do that, and then you change something in the environment, it could be the refractive index, it could be the temperature, it could be the color of the light, or what we call the wavelength. As we do that, by 1 part in 10 to the 3, you can see that it's jumping. Can you see the grainy pattern changes? That's because all the waves, when they add up the crests and troughs and make a pattern, change very, very subtly. And it changes in a beautiful two-dimensional space, not like just two beams. And this turns out to be amazingly sensitive. How sensitive? Today, here in Adelaide, we can do of the order of zeptometers accuracy. Again, I told you 1 second from the age of the universe. We're getting down to knowing timing from the Big Bang to 1 millisecond. That sort of accuracy, but transpose that number, if you like, to the wavelength. These sensors are very, very exciting to measure things in the environment and to measure things even in our healthcare to make some incredible measurements. So let's go back in time again now to, I guess, the time of John Milton. And this is the tale of comets. So Johannes Kepler was a wonderful scientist who talked about the laws of planetary motion. And in between that and protecting his mother from claims of witchcraft, which had quite serious consequences in the 17th century, he also wondered about the tail of a comet. And here you can see the tail of a comet. Oops, no, you can't. Oops. And we know that the tail of a comet points away from the sun. And Kepler wrote this is how he used to write papers, and you can see here, he was writing about the direct rays of the sun hitting the comet, permeating its substance, and throwing something off, and putting on its tail. And this is a hypothetical meeting between him and the philosophy of Elias and Aristotle there on there, looking at the tail of a comet. This actually dates back to an astronomer called Peter Arpin, actually in the 16th century, but Kepler basically said, there's something coming off the sun that's pushing material off the comet. So when you see Halley's comet going around, this wonderful orbit and things are coming off, where is that coming from? And he conjectured there was some kind of solar pressure or solar wind. And we know that light actually does have that. It actually has a wind. So having lived most of my life in Scotland, this is James Clerk Maxwell, probably the most famous Scottish physicist ever. And Maxwell, in one of his equations, wanted to understand how this force of light could be understood. So just like we have a billiard ball, and physicists are obsessed with conservation of properties, like energy and momentum, right? And when you're learning about momentum, you learn about mass times velocity. But light has momentum too, just like that chunk of energy, the photon we described. And Maxwell, doing his mathematics, said, okay, we don't have, the photon momentum is very weak, and we're not going to see anything on the sail of a comet. What can we do on Earth? And he said, you know what we're going to do? We might get an electric lamp and a little disc and shine light on it, and something will go around. And you can buy this on Amazon or eBay. It's called the Crookes radiometer. Maybe you've seen one. Maybe you played around with it. It's a little jar, got a few vanes. You shine a light on it, and the thing goes round. But there's a big problem with the Crookes radiometer for this story, which I got out to say, the problem is it goes around the wrong way. So when you shine it on the shiny side comes towards you. The reason is, actually, does anybody know the reason for that? Top of the class, fantastic. So what happens is the light heats up things, so it gets absorbed, it heats up the molecules. So you have a shiny side and a dark side. The molecules bounce more on this side than that one. So it actually goes around the right, if you like, counterintuitively. But you can buy them and it just take a little vacuum pump and suck the air out or something, and then it will start to go around the correct way. It's a beautiful demonstration of the radiation pressure of light. Today we can get that, but it took, at the turn of the 20th century, by people like Lebedev, Hug, and others, and Nichols, looking at that to see that. So this force is very, very weak of light. It turns out to be of the order of a millionth of a Newton. It's probably equivalent to the gravitational force of attraction between you and your mobile phone. That's how weak this force of light is. So it really shouldn't matter. Shouldn't matter. But in fact, it matters a lot. But like many things in life, you have to find where it matters. So it doesn't matter in this, for me, this force pushing, for example, this camera case over or pulling a wine glass towards me. But if we go down to the size of a cell in my body, or right down to a single atom, because of the way objects scale, so if you halve the diameter of something, it's an eighth as heavy, given its rate of density. It's a volumetric effect, goes as a cube. So that means if you go down to the cell size, red blood cells or atoms, life becomes very, very interesting. And then we use some beautiful laws of Newton, and Newton tells us for every action there's a reaction. So here's a little ball, and it's bending some red light. So it's bending light down, and it's bending light up. You see that bending dip? You go home and you put your hand in the sink, you ever seen how it looks like it's puffed up? That's because of the bending of light as it comes out. So it's like optical illusion, it makes your eyes think that your hand is actually bigger than it is because of the way the light's bent towards your eye. And if you trace back, it seems a bit bigger. Here, in this bending, you can see that the light, the ray at the top is brighter than the one at the bottom. So the ball, this little transparent ball, is bending light down and some light up. But it's bent more light down than up. Now, physicists worry about things like this. They worry about those diagrams. That's not right. Because there was no movement there was no light going up and down before on the left-hand side. Both of the rays were coming this way. But I bent more light down and then up. Am I allowed to do that? Newton says every action has a reaction. So if I made the light go down, the ball's going to go up. So it's going to go to the brightest part of the beam. And that is essentially this. Those are the more diagrams for you if you're interested. This means light can create attractivity. So if you see in science fiction, people say attractivity, you've seen that, right? In many science fiction novels and even on TV, it actually can. But it can't do it at the scale of a spaceship or something that you see that it can do it at the size of a cell or a molecule. So it can hold a little cell very precisely. How important was this? Arthur Ashkin here on the left won half the Nobel Prize in physics in 2018 just for that part. And Gerard Morindon and Strickland won it for, in fact, it's something to do with laser eye surgery and improving laser performance for their getting pulses. But you can see here what that means. So these are little beads or cells in my name, and they're held by light. And you can see the other ones jiggling around, and that's what we call Brownian motion. So when you look under a microscope and you see viruses and small things moving and being agitated by the liquid at room temperature, you can move things. It's like a little tractor beam. But where does that get me? Why would you just give it over much of that? That's fun. But the magic here is this. Optical tweezers ends up solving and helping us in biology in a way. Before 1986, all biological systems, a lot of them with molecular studies, were done with ensembles. But there's a heterogeneity. We would like to study single molecules at one time. That's a single piece of DNA tied in a knot. And there, the little ball that I showed you, which bent light is grabbed by light, another tractor beam grabs too, and in between I tie a piece of DNA. One piece of DNA. And I twist it and I bend it and I see how strong it is. I measure its torsion. I measure its Young's modulus. Here on the bottom, you're seeing kinesin. So if you do biology, you're going to learn that kinesin walks on microtubules and is the porter. It's the thing that carries all your luggage around in the cells. The way it works, kinesin, was actually not understood until optical tweezers resolved the little mechanism, and that mechanism was linked to the conversion of chemical energy to energy by the molecule through ATP to ADP and phosphate. So if you're a biologist, this was revolutionary. It told you how many units of chemical energy needed, and this was used also to understand the basis of motor neuron disease, as an example, the molecular basis. Sadly, we still don't have made progress as much as we'd like in that area, but some quite exciting work is ongoing for us to see. At the other end of the spectrum, including work we're doing here, is there is a complete revolution coming along about the world of quantum. So you hear about quantum in our communication, in sensing, and today people are now already taking objects the size of a red, nearly, well, they're not quite the size of a red blood cell yet, maybe one order of magnitude smaller, and placing them right down at the quantum limit. So this is work just from 2020 to 21. And the idea here is to say, where does the classical world stop and quantum begin? It's a very contentious and interesting question that you should pose and ask. Well, why aren't we in a quantum state now? What stops us being, availing ourselves of all the merits of quantum mechanics, but in a large body? And this is something you can study by using optical traps. Why are optical traps good? Because you're only holding the object with light. It doesn't touch anything. And in the world of quantum, as soon as you touch something, it dissipates, energy dissipates. It's got a route to alleviate its quantum or mysterious nature to somewhere else. So you can start now with seeing already people entangling objects and doing incredible things with these small particles. Light's a complex fellow. It's more complex than sound waves or waves on a skipping rope. It's actually something called it's actually a transverse electromagnetic wave. So just to cut a long story short, what happens is if I'm a light wave moving this way in the plane of my body, there's an electric field going up and down, the magnetic field moving this way, and it has a propagate. Now, how those fields add up can add a little twist. So the light vector, the energy flow, can be actually like a circle, like you see there on the right. And that leads to something called angular momentum, or a twist, as opposed to linear momentum, which we'll never see a force. And if you do that in optical traps, you can spin objects. So here, the twist of light, the magical twist of light, can hold objects and spin them around. Spinning is very, very interesting, rotation. And here, can be used to measure viscosity of incredibly small volumes of fluid, rare biological samples, and many, many things. So here's an example of why spinning is interesting. So many of you spun a top. Have you ever wondered why you can't just hold the top there and then walk away? You have to spin it, otherwise it falls over. It falls over because in physics, we know our conservation laws, and what we do is we give it angular momentum. And that angular momentum must stay with the object. And it conserves it, which means the object has an inherent stability. NASA uses this all the time. If you launch a satellite today, the last thing you want is to see it tumble in a random fashion. So you spin the satellite, and as it spins, it stays in a certain orientation in space. So this is and let's get a little closer to home rather than a spinning top or satellites. This is a video taken on the ISS, International Space Station, about 3 years ago now, and they wanted to do what's called a Hail Mary pass. I guess an AFL pass. So they want to throw a ball right through the International Space Station. You may have seen it, it's a very cool video. And they want to set a world record and get into the Guinness Book of Records and get some media attention. And there you can see the ball going through, and is that a new record? I don't actually know if it was, I'm sure it was. Where else did I get a big thanks for it? So all good. But you know what I really love about this video? Is I love the first 3 or 4 seconds. You know what? Let's go back. Because there, just there, do you see the way they threw the ball? If I gave you an oval-shaped ball, whether you're a rugby player, AFL, you know that if you just did this, you're not going to get very far. All right? If you are Tom Brady, or I don't know, a big AFL player, but in the NFL, you know you're going to have to twist your wrist and give it a bit of a kick. And rotate it. Why do you do that? Do you know what you're doing? You're doing exactly what NASA do. You're doing exactly what happens to spinning top. You're giving the ball some angular momentum. That angular momentum has to stay conserved. So the ball says, I am not going to get perturbed from this direction. So I'm going to have to throw an amazing pass if I get that right. That's how it works. So you're doing that every time you pick up a ball and throw it. So it's really incredible. So why do we even care about this? Work we did, for example, put rotation into those objects at the classical and quantum ground state, and we created the fastest man-made spinning object on Earth at that time. People have gone faster now. That's great to have inspire, and that's what science is all about. Nurturing a community and getting people to push one another in an exciting way, furthering human knowledge. And here you can see that we got something like 5 million rotations per second. So compare that with a little thing that was spinning at 1 or 2 rotations per second there. That little springboard is how we loaded the particle and held it, and then we spun it, and it stays super stable, just like our little ball, and to do that. And why would you do this? We've done some very high precision measurements of torque and force, but they're very big unanswered questions. Many of you may have heard ideas of quantum fluctuations or energy from nothing in the vacuum. There are also proposals to say the vacuum has friction. So if you're going how fast you're going or how fast you're moving, there's nothing slowing you down. Let nothing slow you down, literally. Can you do that? These are unanswered questions that I think this kind of technology will be able to do. And these levitated objects are more sensitive than even the atomic clocks that I mentioned earlier. That's why there's an incredible drive to use them and see where we can go. Finally, on that side, a lot of people are purporting to look for dark matter, dark energy, and gravitational sensors on Earth in experiments that would fit on this table using this technology. So I think within about 10 to 15 years, we will see the first experiments that may sense some aspects of these fields in terrestrial experiments that you may one day be able to visit without having to go walk or see the whole length of light Okay, to be seen. Very exciting time indeed. All right, I'm going to now shift the last part onto light for life. And then I'm going to talk about healthcare and also what we eat and drink. When you say to somebody, is light used in medicine, you don't really hear too much about it. But in fact, this is a picture showing that if you look at the radiological market, it is basically pales in comparison to the optical market that we currently have around the world. This is in 2017, so it's a little bit out of date. But you know, medical lasers, surgery, devices. So incredibly, light is making an enormous impact in all these fields. There's an example of an amazing device that many of you may have actually used at some point, a pulse oximeter, which actually looks at our hemoglobin levels and actually looks at its absorption spectra, 2 wavelengths, and is central to as a precursor to anything that happens in health. But incredibly, light does more than that. So let's look a little bit at the world of microscopy and imaging, because that's where light has made enormous advances. So if we go back to 2008, one of the problems with the biological world is we're basically looking at water. We're looking at things that have very low contrast, just like this water bottle here we've got, and it's very hard to see. That in 2008, because people looked at this beautiful jellyfish, they exploited the genetic component of that, which was luminous. And they could place that into, if you like, the gene of other systems so that we can actually see what's happening. And that beautiful discovery won them the Nobel Prize in chemistry at that time. And what kind of things can you see? This is an example. Here you're seeing the transfer of the HIV virus between 2 cells. Okay. That's an immune cell subset, it's a T cell, and it creates what's called a virological cycle. But by the way, HIV does not go and breathe, or Richard Rebecca laughed too easy, but the big physics here, what's big science, sorry, not physics, biology and chemistry, was actually tagging the virus appropriately with this green fluorescent protein. You can see exactly what happens cell by cell and actually reduce, if you like, these things happening. You can see how important this is coming out post-pandemic to understand the transmission of viruses, and all done using the power of light. We've been working in ways to overcome things such as diffraction. So on the top left, just a little simulation here about what we call diffraction. So diffraction is something that we can't avoid with waves. You stand in the sun, on the street on a sunny day, your shadow isn't sharp. Some of the waves spread out, and it's got a blurry edge. And that blurry and the spread is, if you like, related to the little hole or aperture it goes through. You see, the smaller I make the aperture, the bigger the spread of my waves becomes. And that spread means that when we're imaging things, the resolution can vary across the sample. What I'd really like is a beam of light that was perfectly, a perfect line that could image the same anywhere inside of any organism. That would be very interesting to do. For example, if you took a laser pointer and shone it at the moon, it would actually be 20 or 30 kilometers wide. Even though to you and I in this room, it would seem like an imperfect spot of light that doesn't spread at all. So we've created, and others now around the world, incredible beams of light that trick us into doing these things and doing they don't really disobey the laws of physics, they do over a finite distance. And what you can do is do incredible things with these to see the big scale, because now the light doesn't spread, and the beautiful detail we saw, just like the HIV transmission. I don't know why that's not. So here, we're seeing a Drosophila embryo evolving in real time. This was not seen only in the last 10 years that people managed to see this. On the left, you're seeing cells from a mouse colon to look at colon cancer studies. And I'll just skip on that one. So we can look at the Drosophila embryo to look at the detail that you're starting to see in that image. And here, as I zoom in, you see incredible detail as well as the big field. And that's because we can pattern the shape of the light now in ways that we can actually, as scientists, see, if you like, the whole field of view, the big picture and the small picture all in one. This has revolutionized many areas of developmental biology. It's now being employed in many areas of histopathology. We worked with 2 hospitals to have this used for prostate and also for other cancer studies and also for discovery of colon disease. I'm going to show you this as well. So light need not just give us big pictures, it can also give us molecular information. So instead of using chemistry, we can use light to identify chemical information. And here, when you shine light on a material, not only can you get light, for example, from frozen protein, but it can also excite the atoms and molecules inside the cell's structure. And as the light shines back out at you, it changes energy very slightly. And that change in energy is related to each of the molecular bonds that we actually see. That need not be just used for biology. This is a system that's literally 100 meters from here, and now has been used by a very large company in Europe for spirit studies, and we just completed a study for the Australian Wine Research Institute. This is a real-time video of us analysing, not a biological sample. I come from Scotland, I had some whiskey, I guess. But there you go. That's real-time, how quickly it can tell you. So we have an incredible database that actually tells you which whiskey you're drinking, like that. Now, as a very exciting thing, we actually can now go through the bottle. We have the world's only system that goes through the bottle, and so you don't have to open it. Well, you can, of course, because otherwise what's the point of it? So you can actually open it later, but you might want to be sure that if you buy an expensive wine drink, this artwork's olive oil, you can do that, and there is to remove the confounding effects of the container. So we're working with food and drink manufacturers to see if that's useful, not just for drinks like this, but for also things like lactoferrin, baby powder, and other things. So incredibly, light can make these amazing measurements. If you're an art lover, you may know this painting of For a Farmer's Boy by Winslow Homer. It's actually at the Art Institute in Chicago in the US. There was an enormous debate with the art historians for 20 years that Homer had messed up here and had got the shadowing and sun incorrect on this painting. It's a beautiful story. I can send you the article if you're interested. Raman, or the method that I just showed you, bumped up using a method called surface enhancement, resolved this. Because it showed that painter, Winslow Homer, had used this beautiful pigment that had actually faded away over hundreds of years. And in fact, on the left, he had an autumnal sky with sunset that had actually faded. So the whole meaning of the painting changed because of natural degradation. And this was discovered using optical methods. So for art restoration, it's incredible that you can actually do that without damaging the painting at all. So really, really important for us. So taking care of our cultural heritage is a very important part. So light is a wave, and waves, when you add them up, they do strange things. We're working in the Australian Research Centre of Excellence on frequency codes, where we're looking, if you like, at different space wavelengths of light. But when you add a bunch of them up, they can create these little things that look like what we call wave packets, perhaps, somebody might call them. And they're really a superposition of lots of the waves that you see there. But these little packets of waves can do wonderful things too. And they can do things in backscattering. So one of the most exciting and translatable things in light has been a thing called optical coherence tomography. It's really like ultrasound, but with not ultrasound now, but with light. And here what we do is look at the backscattered light from layers in a sample, as you see over there, and we preferentially want to take sequential slice. It's like an optical biopsy without ever taking anything out of the patient. And this has actually revolutionized ophthalmology in the last 10 years. In fact, I would contend that everybody in this room has either had an OCT scan or will have during the course of their lifetime. It actually is the premier method to pick up macular degenerative disease, glaucoma, and with our changing and aging population is a very, very powerful method. It really can take, obviously you don't want to scalpel anywhere near your retina, but what it does is it takes a beautiful image and picks that up and creates a tolerance. Really revolutionary, and the premier technology we do use all that. Now, it's not only things like the eye that this method can do. Here's my colleague Tom Brown, and we did a little bit of OCT in St Andrews. This system's here now with the the Antarctic division from Tasmania, and they send missions down south from Hobart. There was an interesting problem in climate change. People wanted to understand what was happening to seawater and acidification. Now you can make sophisticated devices, but why not let nature give you some information? And a lot of scientists said the shell thickness of krill under the ice pack vary as a result of the acidification of the ocean. So Tom had a brilliant idea of adapting our OCT system to measure this. And this is what he saw. We developed a beautiful little chip where the krill survived, and we could have a high throughput system to measure their shell thickness and record it and let them swim away. So incredibly, we could build up statistics for something that you really have to basically kill the kill for and measure. So light, in this way, can help us in our societal challenges in ways that we would never thought possible. There's Tom, there's 5 minutes on the email, I guess, at that time, because internet was pretty pricey, what he was doing. So amazing things are happening, including here at Adelaide. This video is from a wonderful colleague of mine, Brett Boom at Mass General Hospital, where he's, this idea of OCT is going beyond ophthalmology, beyond krill, beyond other things, to look at arteriosclerosis, looking at stents. So this can, with a very thin fiber optics, a fraction of the width of a human hair, can be placed inside and take images with stents and look at calcification. It can also be used for the esophagus, as you see here, with these little balloons. So the light beam here is inserted and inflated and there. So that's esophageal cancer as well. I'll very quickly end on this. So one of the topics that seems to be in the news all the time is infertility, and or how the population again is changing, and people are either choosing to have children at later stages in life, or the birth rates in many Western countries are not very high at this time. But also in terms of infertility, that's the definition that we have. And prevalence means that 1 in 6 couples can experience infertility. That's a lot of people worldwide. So there's a social, societal, and scientific need to look at that. Now, there are many, many ways of testing what we call an embryo. And this, look away now, this is a mouse embryo, by the way. So, but this is essentially how a test is done. And so just before implantation, you may need to do genetic sequencing by taking some material and testing it to see if the embryologist says that's the one you're going to pick. And as many of you, I certainly know many friends and colleagues who've been through things such as IVF or assisted reproductive technologies. It's a very daunting, stressful time, as well as the cost. And one doesn't know what's going to happen there. So here, with the reproductive success team led by Kylie Dunning, we've done 2 of the most innovative methods to address this using light. So Kylie started out by addressing with what's called hyperspectral imaging, or basically collecting information from the molecules. You can see that colored picture. She detected what's called aneuploidy, when the number of chromosomes present deviates or is not the ones that you expect. Okay, so we built on that study by making the world's first ever hologram, just like your credit card. of the embryo, all with no surgery at all. The beautiful thing is this can offer the embryologist an additional piece of information, and that beautiful hologram can allow them to see a beautiful 3D rendition. We can not only do a hologram, we can actually tell you what the energetic status is, if you like, of the thing with the metabolic map. So there you go. So we're hoping to build on that to actually allow us to pick the embryo more successfully, to improve that number from sub 20% to something a little bit more. So I'll finish now. We're lighting a new pump. I think the person on this picture is actually in the audience here today. David, he featured quite heavily in that lovely brochure. This is free to download. It tells you about the opportunities. There's some numbers. I won't dwell on them because everybody can read that and look at it. But you can see that South Australia is becoming a beacon for exciting photonics. And as Ban Ki-moon, when he launched the International Year of Light, said, as in this century, we're looking for shared prosperity, and light technologies offer an incredible avenue for that. So I'll stop there. I hope in that little whistle-stop tour, I've given you some excitement and some surprises about the really incredible impact of light right across technology. And there's so many things I've not touched on, like the internet and communication and so many things. But I hope you've got a flavor, and there's something that I believe everything I've shown you is interconnected. That's why I work in so many areas. You may think they're disparate, they're not. The beauty is science is connected, and science is changing under our very feet. All right? Year on year, it might be incremental, but today we take gravitational waves for granted. There's one example. Today, if somebody had told me 30 years ago I could sit here with a phone and pick up a movie on my phone with no wires, I would have laughed. But we take it for granted. What's next? Let's hope the great things that come change things for the good for all of us, and inspire lots of people to join me and others in this quest to do great things for the planet. Okay, with that I'll stop, and thank you all for your kind attention.
All right, thank you very much for that fantastic talk, Kishan. So I'll briefly open the floor to questions. If anyone has any questions about the presentation or the things they'd like to ask Kishan, just stick your hand up, I'll run around and hand the mic out. So if anyone has any questions, please feel free.
Thank you, Dr. Kishan. I'd like to ask, when we saw the imaging using light to trap particles, did the observation not intervene? Like we're still using light to look at those particles, or have I got this wrong?
Okay, so brilliant question. So I'll just repeat the question if I may say, but the question is, does the light that I use in the microscope or just to illuminate the sample, does that not interfere with the optical trapping process itself? And the answer is it doesn't, because if you look at the parallel, to trap something, I actually need a laser that's focused to a small spot. So the power there, I would maybe take a laser pointer and focus it down. The power levels used for that, power per unit area, are much orders of magnitude higher than the light from the ambient illumination. But it's absolutely true. There will be a very small force, but it'll be overwhelmed by the force of the light focusing down and grabbing that little tractor beam. But an excellent question, and one we've actually worried about in our research experiments as well. Thank you.
In one of your examples of applications of lasers, you mentioned an experiment where, like 10 years ago, they measured a very tiny amount of force. I did a quick Google search, and most of the results was still that same article from 10 years ago. And I'm just wondering if there's been any progress made in terms of measuring even tinier forces.
Tinier forces. So I'm not sure which measurement you made.
It was the experiment from 2014 in that they used a laser to measure like tiny gravitational forces.
Okay, so they have not. So well, maybe we'll talk about this offline, but if you forward size that, if it was the one on the gravitational waves, is that the one? No, not that one. That's not been measured experimentally yet. That's a proposal experiment in 2014. So maybe that's where, if it's another experiment in terms of optical tweezers, then people have measured down to attometers. The problem there is the resolution that you can get. So you kind of plateau because we have current camera technology, imaging technology as well. So there's sources of noise in these experiments, which is one thing, for example, like LIGO worked very hard to get to the floor. So just because the experiment was 10 years ago doesn't mean we can't improve it, but the problem is getting, if you like, things like noise levels down, and there might be, the effort to do that might be too much for the payback. You've also got to think, what are you trying to measure and how big it is? So if you already can measure things fantastically at a femtometer or an attometer, that's great, let's stick with it, let's do some new measurements. Okay, it's a very good question, and I think you're right, because you want to keep that number coming down, 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 but then also maybe to equate that to what the gravitational force is, and whether you really need to take the force into account.
Are there any more questions?
Yes, thank you for shedding some light on this topic. It's very interesting. The crazy atto-Newton measurements, what the very weak force measurement. Perhaps I missed something there. How do you actually measure the force? Once you've got the particle very well
Excellent question.
how do you turn it into a force measurement? How do you get information out of it?
Okay, so the question is, if I hold an object in optical tweezers or whatever, how do I turn something that's held with light into something that is a force transducer? So what I really need is something like you might use on the wheel of your car. I guess nobody changes with tires anymore, but in the old days, like, you have to take the bolts off and try to, yeah. So what happens is that you calibrate the system. So what happens is the light creates, if you like, a ball. Imagine a marble in a bowl, and it's wiggling around, and the bowl, it moves up the side of the bowl is parabolic, so force is proportional to displacement. And that constant, the spring constant, if you like, of the trap, is what you calibrate. So it's like a little Hookean spring. And once you know the displacement, then something comes along and tugs it, and then you know the displacement, you know the constant proportionality, you can convert it to a force.
And the weaker you hold it, the more easily it moves.
That's correct.
That's a very cool system.
Yes, that's right. So in fact, holding it very gently is actually sometimes very good. But then, you have more potential for Brownian noise or Brownian motion, creating noise on the measurement. But these are little trade-offs, one of these to think about.
Are there any more questions?
Can you use light to view the quantum state of an atom, or just the atom itself?
What a brilliant question. So I'll repeat the question, if I may, if that's it. And so to correct me if I said, can I use light to view the quantum state of an atom, or just the atom itself? Is that right? Is that what you're saying? Yeah, so, okay, so when you look at how am I going to answer this? Okay, so I guess you're coming from a point of view, when you look at something in quantum mechanics, you collapse the wave function. So in other words, if you have like entanglement or something, as soon as you make a measurement or read out, it collapses to one state or another. So the normal answer is yes, you do collapse it, okay, in normal measurements. There are some elaborate schemes that are called weak measurements and other things where you can kind of keep like the quantum nature of it. But the question then is, what do you actually measure? What are you really measuring? You still measuring the superposition state. In the particle as well, that's you can also do measurements like that, but usually you do you're absolutely like collapse the wave function. So measurement is really at the measurement principle is the harder function. Nearly in all cases, you need to read out the system, I guess, at each time, and then you can repair the system in the quantum state again.
Okay, are there any more questions? If not, then I'll just get everyone to thank Kishan again for the talk.